I would like to welcome our speaker, Yancho Gerdjikov, the Manager of Emerging Technologies in IT at Nestle Americas, where he leads innovative initiatives across AI, XR, blockchain, quantum computing, and transformative tech strategy. And he has over 15 years of international experience, and he has held key roles in cybersecurity leadership in North America, global IT audit, and piloting emerging technologies across Nestle's operations. He holds a degree in aeronautical engineering and has completed executive programs in Harvard in business communication and cyber risk. Welcome to the program, Yancho. Over to you.
Hello, everyone. Thanks for having me. It's a pleasure to be here. Thanks for the invite. After I met Prachi at Quantum Tech, I learned about this community, and I'm very excited to share with you what we did last summer. So let me share my presentation. So without more delays, we're going to talk about order fulfillment and how we used QAOA. We try to optimize our existing process. But just a couple of slides before we dive into this. So why we decided that it's time to act now, what use cases we are looking at, and what we call the translation problem is kind of the main things I want to talk to you about today. So why we decided to act now is because we know we're in the NISC era, but we think that this era is coming to an end. So we are no longer right the early days of aviation. It's more like the first airplanes that really paved the way for the golden era of aviation. And different companies have different expectations, but we see more and more aggressive roadmaps. So already last year we knew that it's about time to get involved more seriously, and we looked for a use case to pilot. And we were lucky that supply chain was supportive, and we got an opportunity to try to improve the order fulfillment process. So what are the use cases that we think going to bring value to an organization like ours? We try to categorize them by type of problems and by function. So probably for this community, it will be very clear that combinatorial problems and forecasting and classification problems would be applicable. Not so much in the enterprise. I can tell you that we are now trying to raise awareness and show people where this technology can be utilized, in which parts of the existing workflows it can add value. And then by function, we believe that in our logistics, in finance, and in R&D are the primary areas where it can be useful, and probably there are other adjacent fields. But for now, the priority is really logistics and finance and R&D. And the thing that we did try last summer was a process called distributed order management. And this is something that Nestle is doing for decades, but we never tried to solve it with a quantum computer before. And we've always tried with classical methods. And we have had success so far, but we are never close to the optimal solution. So let me explain what this means. We have a process that is determining how to fulfill each order at the lowest possible shipping cost. And this is happening for maybe 90+% of all the orders. And there are many, there are tens of thousands of orders daily. Some part of those orders, some fraction, would not be fulfilled by their default distribution center. And this is where you have to choose what is your best option. You have a big network with many distribution centers, and there is different inventory in each distribution center, and different lead time, and different dock availability, and a bunch of constraints. So picking the best option to fulfill your order impacts a lot how much revenue you're going to bring. Are you going to be on time? Do you face a penalty from a customer? How much will be your shipping cost, and so on? So the way we solve this classically, and I have some slides later to illustrate that, is by creating an objective function and then solving this objective function order by order, by listing every possible option for each order and then selecting the most promising one. It is a slow process. Currently, we are doing it in Azure. We have a Databricks notebook that has the logic and is combing through the orders and then is proposing to the planners the best way to fulfill the orders. Again, this is a small fraction of all the orders. This is why you see that there are like a couple of hundred a day that need to be handled this way, and this is only the fraction that cannot be fulfilled by the default distribution center. So the outcome was that we managed to, so we knew first why we started with this process is that we had a reference. We knew how to solve it. We had the objective function. We also knew how long it takes to be solved classically and how much more revenue we are bringing if we take the proposals from the optimizer. So we could compare the quantum solution and see if it is achieving the same savings or increase in revenue and if it is faster. And we expected it to be more expensive, we just didn't know how much more. So the outcome was that we did manage to save as much as we saved with the classical solver, which was around 5%. And it was taking approximately the same time because we could only process in batches and it was slower. This way we could not handle 100 orders at a time. It was impossible. And it was way more expensive, like 1,000 times more expensive. So we concluded that it is not feasible for business, real life business problems today. It just doesn't scale. But based on everything we learned about quantum computing and what is going on outside in the field, we expected that in about 5 years, we would have a realistic chance to bring value, to have a return on this investment. Additional thing that was not expected was that we found a superior classical algorithm called branch and price, which I was not aware of. It's like 20-year-old algorithm, which can speed up our processing by a factor of 3, which is pretty good. So the function I was talking about, basically in this tabular data, you have the sales and the penalties and a bunch of other things. So if you subtract the shipping costs and penalty means if you try to sell to Walmart, we're not talking about orders to individuals, but orders to retailers, which would have thousands of items in them, and you have contractual obligations to fill at least 90% of each order or 85 or whatever the agreement is. If you don't meet the expectation, you're subject to penalties. So the objective function is the sales minus penalty and shipping cost, and this should be the biggest possible number. This is what we were solving classically by listing all possible options and picking the best one. And there are many additional constraints, like this FTL here is for full truckload. This has to do with the shipping cost. If you fill the trucks, you can move more stock with less travels. And then when we did this hybrid approach, basically the data at the end looked like this. You have the optimized and the default value. So this for the distribution center, the objective function. You can see here that the optimized value is higher by this amount because we can fill more of the orders, so 90% versus 6,800 versus 62, etc. And then what are the sales related to it? And then the penalties, here we would face this amount of penalty, here it's lower, and this is the shipping if it's optimized and so on. So even though it's more expensive to ship because you face less penalties and you bring in more revenue, it makes more sense to pick this option. So those type of decisions are what we are hoping we can very quickly make efficiently with quantum computer. So how did we do this? I guess that's very clear for your community, but we used QAOA, where we would feed the function and then run it to a quantum computer, pass the parameters to an optimizer, and then iterate until we find good option. And why we choose QAOA is because we can use it with today's NISC devices, and you can account for all the constraints that you have to observe through penalty terms. So in practice, it results in number of columns that are generated, which inform the decision from which distribution center we should fill each order. And we, following the branch and price algorithm, created a relaxed version of the master problem, and then all the possible solutions we compare, and the promising ones that result in some improvement we store as lower bounds until we come to a point where there is no more improvement, and then we attempt to solve the full master problem. And doing this, we achieved the following results. So if we use just a classical solver, you can see it takes like an hour to process 40 orders. If we use branch and price, it's comparable. But if we break it into chunks and run in parallel, we decrease it to about under 10 minutes. So that was pretty good. And then still it was not enough for our needs. So we estimated the threshold is when you can process batches of about 110 orders. If you can do that, then you would be able to handle the demands of the business today for just this one business that we have, Nestle USA. We're not talking about the other operating company that Nestle has in North America. It would need bigger devices, or maybe more jobs run in parallel, and so on. And that was 1 year ago. So perhaps if we do it today, it will be much better. So now what we call a translation problem, and I think that this was the main learning from us and probably the main value. We got a good reality check about what is doable today. But what is more important, even we learned how much it would take to translate an idea into an algorithm you can solve on a quantum computer. So we start with the idea, which is this thing: you have some orders, you have inventory for 700 of them, you don't have for 400. For some, you cannot even fill a complete truck. And you just select the ones that you can. Your objective is to fill complete trucks every time. So if you take this idea, the mathematical formulation looks like this. This is exactly the objective function that we solved. That would be the revenue, this would be the pallets, this would be the individual SKUs, this would be the cases that you have to fill, this is the removing the shipping cost, removing the penalties. It's exactly this type of formulation. And this is not easy for us to do. We can do it internally. We have people that are trained to do those type of things. But even if we do this, we still have to convert this into binary options, so we can encode it in qubits and select the best option. And only after this we can write the algorithm and then get the tabular data. So maybe for a research community, this is not so much of a headache, but for pretty much every company out there that's not specializing in quantum computing, that's quite a steep learning curve. And it will take a while to get there. And there is no ambition to solve everything in-house, not at all, but at least to be adequate in the process. So because we learned what it takes, we immediately focused on creating awareness and spotting key people that need training and so on. And to give you an idea, for our 110 orders that would make it relevant to the business, it would require 2,500 qubits and 30,000 gates. So you can imagine, again, this is a small part of a business problem that we are solving. So you can imagine what will be the complexity if we attempt to solve the problems that are relevant for the scale of our organization. So again, the translation problem, how does it work? We need the business here, the idea. Then we have to do a mathematical formulation of the objective function, select the algorithm. So that's our branch and price that we used for the QAOA. And then create the quantum algorithm and then interpret the results. So who are the parties involved? You means the business, and us means our innovation team and maybe data analytics or experts in supply chain or in finance or the respective function that's hosting the problem. And then for the quantum algorithm part, we use partners. And from our perspective, it's all about the quantum software. The hardware is going to be just SaaS for us. I have not heard anyone of talking about in-house quantum computer. So it's all about the software to make it as easy as possible, lower the barrier so more people can understand what this is, and more people can participate in use cases and address business problems. And then analyzing is, for everyone. So we have a crowdsourcing in-house. We are collecting ideas. This here a call to action for those guys. And then I guess the last thing I want to mention is we are aware that there are many, stakeholders. So all of our internal stakeholders and then external stakeholders, and there is so much happening in the ecosystem alone. I have this is not an exhaustive list, but as you know, there are many networks like yours. There are many companies, and we are discovering our options and looking to create fruitful partnerships for both and the others involved. I believe that is my last slide. So thank you for your attention.
Yeah, thank you so much, Yancho. We have a few questions coming on Discord for you, and I can just read them out. Okay, we have a question from Ron Schreiner in Chicago. Are you using a quantum algorithm to pick the best process for all orders, or is the intent to use a quantum algorithm for each discrete order?
It is a quantum algorithm that is picking the best option to fulfill each order. So if you have, imagine 5 distribution centers, and you have one order to fulfill, and you can fulfill it from all 5, but with different shipping costs and different lead times. So in one you may have penalty, in others not. Our task is to pick the distribution center from which this order will bring the maximum revenue and have the lowest shipping cost and penalty.
Thank you. Yeah, we have a question from Cheryl. If we can have the link for the open source crowdsourcing.
This is in-house crowdsourcing. This
So
is
it's not
for
open
Nestle, for Nestle employees only, to give ideas. Like if you're in supply chain and you have another combinatorial problem, let us know.
Got it. Thank you. Okay, we have a few questions from Mohammad Reza in Iran. So question 1, it was apparently demonstrated that quantum annealing almost always outperforms the PQC-based combinatorial optimization schemes. Is there a solid immediate reason for that? For example, the all-encompassing presence of QUBO and direct translation.
I'm not sure I understand completely the question. Is the question why annealers are outperforming other quantum computers?
Yeah, why annealers are outperforming PQC-based combinatorial optimization schemes.
I don't think I'm qualified to answer this. That's too technical for me. I'm not an expert in quantum computing, so I'm sorry, but I do appreciate the comment because there is this company called D-Wave that, as you all know, is building computers based on annealers. And from all the companies we've spoken to, they're the only one I hear saying that they can achieve advantage now with their annealer technology, specifically for optimization problems. So this is something that we are yet to explore. It's on my to-do list, but I honestly don't know why they are superior. Is it an algorithmic advantage? Is it something else that is the reason? I cannot answer.
Okay, thank you. Another follow-up question. So in the project that you just presented, did you do like a comparison of the performance over the various modalities for QAOA? And if so, what were the results?
No, I don't think we did that. We just picked one formulation that would work for us and compared strictly against the classical solution. Our primary objective was to assess the business feasibility, which is based on cost, speed, and accuracy. So this is what we focused on. We understood that the accuracy is on par with the classical solution. That's why we could bring the same amount of saving. We understood what is the time it takes to process the orders because we have the run times from our classical job. And we also understood what is the cost related to it. So our objective was to estimate how much it differs from the classical solution that we have today and when we can expect this to be viable for business solution. It was just that.
Mhm. Okay, thank you. We have a question from Elizabeth in USA. So,
Mhm.
given the complexity of encoding real-world constraints like the FTL truck loading, how did you decide which constraints to include in the QBO formulation from your slide?
With the help of subject matter expert from supply chain. So we spent probably the most time to formulate the objective function first, make sure we understand all the constraints, not just the full truckloads, but also the replenishment routines and the dock availability and all of the things that we could think of and that the subject matter expert would tell us. And only after the objective function was written in a way that no one from the team could think of something that we have forgotten, then we moved to the next step to create the QBO formulation, again with the same approach, having the engineers from the agency we work with explain what will be the impact of including this or that, and then asking the subject matter expert if this makes sense operationally.
Thank you. Would you say that like some constraints were harder to encode than other constraints?
Specifically, the replenishment routine, we had to just accept a heuristic. There wasn't a way to encode it directly. There wasn't a strict rule by which replenishment happened. It was varying business by business, and this created a lot of complexity. For instance, when I explain this, it's not one business. There is the frozen products, then there is the chill products, ambient products, then there is specific networks for the pet food and different network for the coffees, and it is just too many things to consider. So we had to use a simplified heuristic to deal with this.
Thank you. We have another kind of technical question. So do you have insights on how to balance the fidelity versus circuit depth on today's limited qubit count missions?
I couldn't answer this either. I'm sorry if this is disappointing for you guys, but I am just not prepared enough to speak about those highly technical in my mind aspects of the quantum computing.
No, that's okay. Thank you so much. It's like we have projects that participants work with our industry affiliates also. So I think they're relating your talk with their specific application problem. And so they have all these deep questions for you.
Yeah.
Oh,
Well, as I said in the slides, when it comes to creating the quantum circuit, we relied on partners. We have uh, a couple of people that have PhD in quantum physics in Nestle, and Jordan Moore's one of them. He's leading the efforts actually. So I guess they would be able to answer this. For me, it's not possible now.
That's all right. Thank you. Maybe I can ask you some high-level questions on what kind of advice would you have for people starting research projects, working in application-specific problems, and how do they approach the problem? Where do they start with? What are your thoughts on that?
So what was very helpful for me was understanding the operational problem, the real business problem, and trying to imagine exactly what is happening in the physical world. Like Walmart orders 5,000 items from 3 different categories where we play. Where is the product? Is it in boxes, in pallets, in how many places? What does it take to move this product from our warehouse to the shelf in Walmart? I go through all the physical steps. So once I understood what is the objective, then when I saw the mathematical formulation and then the QAOA formulation, and I was asking questions to the people writing those, I could follow along because I understood the physical process. So for me, understanding the task at hand was very helpful to follow along. And I would advise that whatever is the problem that you're addressing, you should be able to imagine in details what this means before you even start trying to write objective functions and all of those things that are needed.
Thank you. That was a very, very good advice. What other kind of application problems are you interested in, Nestle?
Oh, as I said, research and development, this is whole area, for instance, optimizing our recipes. It is very similar combinatorial problem. Like which type of sugar, which type of cocoa, which type of oil, how to, you can, I bet, create an objective function that holds specific features for the product, like how it would taste and what will be the texture and this and that, and then select options how to get there. So that is one big area of research. Nestle has hundreds of thousands of different products, so you can imagine the space is very big.
Mhm. Yeah, thank you so much. At the ending of the session. Oh, we got one last question. So you mentioned using full truckloads. So did
Mhm.
you also test with combinations like trains and truck or shipping by air and trucks?
It was just trucks. We didn't have data. In the US, it's mainly by trucks. It's ground transportation. That's the way it works.
Okay, thank you. Yeah, we also have a comment from Cheryl. She enjoyed seeing how quantum can be used in real world problems for businesses. And the same for me. It was very insightful. Thank you so much.
You're very welcome. So if you can do anything to make the translation problem easier, maybe if there is compiler, maybe something like the way people write code with cursor today or with GitHub Copilot to write the quantum circuits and then make it understandable, user-friendly, I think that would help pretty much everyone that is involved. You still would need expertise to understand the solution. It's like asking ChatGPT to create a mobile app for you or a website. It will do it, but then if you need to change anything and you don't understand how to read the code, you're lost. So I get it, but it seems so rudimentary. It's like writing assembler code, like giving electric pose instructions to the microchips is the kind of analogy I have in my mind when I see the quantum circuit code. So yeah, for communities like yours, I guess that would be pretty useful, much more useful in my mind than solving any specific industry problem.
Thank you. That's very good to know. Yeah, thank you once again for joining us today and for your very insightful presentation on how it can be used for real world applications.
Of course, my pleasure. Enjoy the rest.